Hello everyone, welcome to Indian National Junior Science Olympiad 2017 Physics Solutions. In an old Sherlock Holmes movie, a criminal kept a 12.5 centimeter long knife, mass 1 kg, in a 15 centimeter thick book, excluding the thickness of the cover, with a spring trap. The spring has 25 turns, each 1 mm thick. The spring is fixed at the back cover and a knife presses the spring to its maximum when the front cover is closed so that the turns touch each other. The design is such that if the book is held in front of the body and opened, the knife gets detached from the spring and hits the reader, that is Sherlock Holmes in this case. Unstretched length of the spring is equal to thickness of the book. However, Sherlock Holmes was too smart and hence he opened the book in such a way that the knife flew vertically upwards. All the energy of the spring is given to the knife, which just reached the ceiling at a height of 5 meters from the tip of the knife and got stuck there. Calculate the spring constant, which satisfies the equation F equal to minus kx. Applying conservation of mechanical energy, kinetic energy given to the knife equal to mgh, that is 1 into 10 into 5, that is 50 joule. Unstretched length of the spring equal to 15 centimeter. Compression in the spring, that is unstretched length minus thickness, that comes out to be 15 minus 2.5, that is 0.125 meter. Elastic potential energy stored in the spring is a half kx square, that is half into k into 0.125 whole square. Applying conservation of energy, half into k into 0.125 whole square equal to 50, from which we get k value as 6.4 Newton per millimeter. The focal length of a biconvex lens made of a soft material can be changed by changing its shape. An object was brought from far away to near the biconvex lens. For each option given below, the first, that is left side graph, gives dependence of 1 by v on 1 by u as the shape of the lens is changed, and the second graph gives the corresponding dependence of f on u. Here u, v, f have standard meanings and all the images are real. Which of the following options is a correct representation of that lens? Applying lens formula, 1 by v minus 1 by u equal to 1 by f. For convex lens real image, it is 1 by v plus 1 by u equal to 1 by f, which gives us 1 by v equal to minus 1 by u plus 1 by f, which is in the form of y equal to x plus a. Here a equal to 1 by f is changed by changing the shape of the lens, so the equation is a straight line passing through origin. Apply Lensmaker's formula, 1 by f equal to mu minus 1 of 1 by r1 minus 1 by r2. The focal length of the lens depends on refractive index of the material and the radii of curvature. It is independent of the object distance and image distances, so the graph should be a straight line. In a laboratory, a plane mirror and a student move with velocities as shown in figure. X and y components of the velocities in meter per second of the image of the student as seen by the student are respectively. See the diagram carefully. Y component of student's velocity is 10 sin 60, which is 5 root 3 meter per second. Y component of mirror velocity is 5 sin 30, that is 2.5 meter per second. X component of student's velocity is 10 cos 60, that is 5 meter per second. X component of mirror velocity is 5 cos 30, that is 2.5 root 3 meter per second. Velocity of the image with respect to mirror equal to minus velocity of the object with respect to mirror. So velocity of image minus velocity of mirror equal to minus of velocity of object minus velocity of mirror, from which we get velocity of image plus velocity of object equal to 2 times velocity of mirror. So velocity of image equal to 2vm minus v0, which is minus 5 root 3 minus 5. Velocity of image with respect to observer, that is VIO equal to VI minus V0, that is minus 5 root 3 minus 5 minus 5, which comes out to be minus 5 root 3 minus 10. So velocity of image with respect to observer is minus 5 times 2 plus root 3. While driving on a level road at 72 kmph, Vinayak observes the traffic signal turning red, the white stopping line being 52 meters away from the front end of the car. Immediately he applies brakes that decelerate the car at 4 meters per second square. How far from the stopping line will the front end of the car be after 6 seconds? Initial speed of the car is 72 kmph, that is 20 meter per second. Deceleration of the car is 4 meter per second square. Distance travelled in 6 seconds, S equal to ut minus half at square, which comes out to be 48 meter. So the distance of the front end of the car from the stopping line is 52 minus 48, that is 4 meter. A convex mirror of radius of curvature 12 cm has its principal axis horizontal. A simple pendulum with a tiny bob oscillating in front of the mirror such that the center of mass of the bob is 12 cm away from the mirror along the principal axis. Amplitude of oscillation is 3 cm and there is practically no damping. Length of the pendulum is sufficiently large and the plane of oscillation is such that the bob moves practically along the principal axis of the mirror. Path length of the image of the bob formed by the mirror is. Focal length of the mirror is half of radius of curvature, which is 6 cm. Object distance is 12 cm. Amplitude of oscillation is given to be 3 cm. Applying mirror formula 1 by V plus 1 by U equal to 1 by F, from which 1 by V equal to 1 by U plus 1 by F, because for a convex mirror object distance is negative. Image distance corresponding to U equal to 9 cm is 3.6 cm. Image distance corresponding to U equal to 15 cm is 4.3 cm. So the path length of the image V2 minus V1, that is 4.3 minus 3.6, which comes out to be 0.7 cm. A point source of light B is placed at a distance D in front of the center of a mirror of a horizontal length L fixed on a wall. A man walks in front of the mirror and parallel to it at a distance of 2D from it as shown in figure. The greatest distance over which he can see the image of the light source in the mirror is. See the diagrams carefully. From the diagram, MNO and MPQ are similar triangles. So Mn by Mq equal to Nq by Qp, that is D by 2D equal to L by 2x, which gives us L equal to x. So the greatest distance over which the man can see the image of the light source in the mirror is L plus x right plus x left, that is 3L. Here the diagram is represented for only the right hand side. A sound wave of fixed frequency is going through a medium in x direction. Ignore the velocities of the particles due to thermal motion and assume that the layers of the medium perform SHM about their mean position. Graph in figure represents displacements of the particles from their mean position plotted on y-axis at a particular instant of time. Some of the particles are labeled by alphabets A to S. Velocity of the particle G is directed negative at that instant. Points C, I and O correspond to maximum displacement at that instant. Statement 1. The sound wave is traveling along negative x direction. The sound wave is traveling along positive x direction. Particles C, I and O are possessing maximum kinetic energy at the given instant. Particles F, L and R possessing maximum kinetic energy at the given instant. Relation between wave velocity and particle velocity. Velocity of the particle equal to negative slope of velocity of the wave. So the velocity of the particle at G is negative. Slope of the wave at that point is also negative. So the velocity of the wave is negative. The wave is traveling along negative x-axis. Kinetic energy of the particle is half mv square. From the above relation, velocity of the particle is proportional to slope as velocity of the wave in a given medium is constant. Points F, L and R have maximum slope in the given curve. So the particles have maximum kinetic energy at these points. 7 1 ohm resistors are connected as shown. Resistance of the conducting wires is negligible. Effective resistance between A and B is. In the given figure, PQ is a long uniform coil of metal wire, V is a constant voltage source, and ASB is a rheostat. Consider the following statements and choose the correct options. The pole at P, if slider S of rheostat is moved from A to B, is north. The pole at P, if slider S of rheostat is moved from A to B, is south. The pole at P, if slider S of rheostat is moved from B to A, is north. The pole at P, if the slider S of rheostat is moved from B to A, is south. When the slider is moved from A to B, resistance is included in the circuit, thus reducing the current. As the slider is moved from B to A, resistance is removed from the circuit, thus increasing the current. Here the effect of slider is to increase or decrease the current but not to change its direction. Pole configuration at the ends changes when the direction of current changes but not in magnitude. So at the end P behaves as a south pole in both cases as current is flowing in clockwise direction in it. So the correct option is C. An earthen pot was filled with 20 liters of water at room temperature 25 degrees centigrade and left closed. After some time, it was found that the temperature of the water has dropped by 5 degrees centigrade while the temperature of the surrounding and the pot remained same. How much is the amount of water remaining in the pot? Let the mass of water evaporated be M. Amount of heat energy absorbed during the process Q equal to ml, that is 540 m calorie. Decrease in temperature of water is given to be 5 degrees centigrade. Amount of heat energy removed from water Q dash equal to ms delta T, that is 20 into 1000 into 1 into 5, which is 10 power 5 calorie. For the mass of evaporated water Q equal to Q dash, that is 540 m equal to 10 power 5, which gives us 185.2 gram. Amount of water remaining in the pot is 20,000 minus 185.2, that is 19.8 liter. You know, in the case of water, 1 kg equal to 1 liter. To get a significant amount of photons of wavelength lambda from an LED, the minimum voltage across the LED should be able to increase the energy of electrons by an amount equal to the energy of photons, that is E equal to Hc by lambda. The value of Hc can be taken as 1250 electron volt nanometer. A voltage V applied across an LED raises the energy of the electron by V electron volt. Light emitting diode of a particular brand glows with a significant brightness if 20 mA current passes through it. While conducting, its resistance is practically negligible. Once proper voltage exists across it, a circuit is made as shown in figure. There is a fixed series resistance of 40 ohm for the purpose of limiting the current and a 5 volts battery is used. Assume that the voltage across the LED is the minimum required to raise the energy of the electron equal to the energy of light photon needed. Estimate the resistance range of the rheostat if light from wavelength 625 nanometer, that is orange red, to 500 nanometer, that is green cyan, is to be emitted by the LED. Energy corresponding to orange red light E equal to Hc by lambda, that is 1250 by 625, which comes out to be 2 electron volt. Energy corresponding to green cyan light is 2.5 electron volt. Current through the diode is 20 milliampere. Voltage across the diode for orange red light is 2 volt. Applying KVL, minus IR minus VD minus I into RH plus 5 equal to 0, which gives us a resistance of the rheostat to be 110 ohm. Voltage across the diode for green cyan light is 2.5 volt. So applying KVL again, we get a rheostat resistance to be 85 ohm. So the range of resistances of the rheostat should be 85 ohm to 110 ohm. In the circuit diagram shown, on removing the resistor R, it is necessary to have an additional 6 ohms resistance in series with the 6 ohm resistance so that the current through 80 ohm resistor is unchanged. Determine R. Initial current through the circuit I1 equal to 5 by 6 plus 8R by 8 plus R, which is 40 plus 5R by 48 plus 14R. Initial current through 8 ohms resistance I8 initial is R by R plus 8 into I1 that is r by r plus 8 into 40 plus 5r by 48 plus 14r, which is 5r by 48 plus 14r. You know, in parallel combination, current divides in the inverse ratio of resistances. Final current through 8 ohms resistance, I8 final is 5 by 20, that is 1 by 4. Given I8 initial equal to I8 final, so 5R by 48 plus 14R equal to 0.25, which gives us R equal to 8 ohms. A battery of mobile phone of rating 3.6 volt 3600 milliampere hour loses its complete charge in 24 hours when connected to a mesh on the largest diagonal points between A and C or between B and D as shown below. What is the value of resistance of the individual arm? All arms have same resistance. How long will the battery last if it is connected across one of the outer arms, say DC, CB or AB or BC? Assume that the battery voltage remains constant throughout its discharge. Rating of the battery 3.6 volt 3600 milliampere hour. When the battery is connected between B and D, the joint at O can be removed. Then the circuit simplifies to as shown in figure. Effective resistance between B and D is 1.5 R. Current through the circuit is 12 by 5 R. Lifetime of the battery, that is current rating by current, that is 3.6 into 5 R by 12, from which we get R equal to 16 ohm. When the battery is connected between A and B, then the circuit simplifies to the figure as shown. Effective resistance between A and B is 5 by 4 ohm. Current through the circuit I equal to 3.6 into 4 by 5R, which is 180 milliampere. So the lifetime of the battery T equal to current rating by current again, it is 3600 by 180, which comes out to be 20 hours. A 7 meter long uniform rope of mass 140 gram is hanging freely from a ceiling. A transverse pulse is generated at the free end which travels up to the top. Speed of the wave along a string is given by V equal to root T by lambda, where T is tension in the string and lambda is linear density. Using G equal to 10 meter per second square, calculate the speed of the pulse at 5 different distances at every 1 meter from the free end. Plot variation of speed against distance from the bottom. Using your graph, determine the speed of the pulse at the midpoint of the string. Speed of transverse wave on a string V equal to root by lambda. As the string is vertical, the tension in the string increases as one goes from bottom end to the top. So the speed also varies. V equal to root T by lambda. T is mg, so it is root mg by lambda. Mass can be written as linear density into distance. So it is lambda x g by lambda, which is root gx. So V is proportional to root x. So the speed of the wave pulse at midpoint will be V equal to root of 10 into 3.5, that is 5.9, approximately 6 meter per second. You can see the graph in this frame where we have taken the values of speed corresponding to the values of position, that is starting from bottom end 0 to 6 meter. So the speeds are given and the graphical representation is given. So from the graph you can see it is almost a linear increase. From the graph also we can find the speed of the wave pulse, which almost coincides with the theoretical calculation.